Hydrogen purification is a precise and demanding process. It requires filtration systems that can maintain exceptional gas purity without compromising operational efficiency. And within these systems, both pressure drop and flow rate work together to determine how effectively a filter can remove contaminants while sustaining throughput. Understanding how these elements interact is key for engineers, operators, and system designers tasked with optimizing hydrogen production and purification lines. When pressure drop and flow rate are properly balanced, a hydrogen purification filter can achieve maximum efficiency, which includes removing contaminants, maintaining product purity, and reducing strain on upstream or downstream components. However, neglecting this balance can lead to reduced filter life, higher operating costs, and even compromised gas quality. Pressure drop is a measurable decrease in gas pressure as hydrogen flows through a filter element. In a hydrogen purification system, this occurs because the filter media and internal flow paths introduce resistance to movement. While this resistance is necessary for capturing particles, aerosols, or catalyst dust, it also means the gas loses some of its purity energy before exiting the filter. For hydrogen producers, understanding the phenomenon is not only critical to maintaining efficiency, but also to avoid costly downtime or system failures caused by excessive restriction. Several factors influence pressure drop in purification filters. Media type and density play a major role as finer mesh or thicker material structures capture smaller particles but cause higher resistance to flow. Contaminant loading is another major contributor over time, as debris accumulates within the filter media and the available pathways for gas movement narrows, which increases the drop. Even filter geometry and housing design can significantly impact how hydrogen moves through the system. A healthy, controlled pressure drop is actually a sign of proper filtration, as it means the filter is engaging with the gas stream and removing unwanted particles. However, excessive pressure drop signals a problem. Excessive pressure drop can indicate a problem such as the filter being clogged, improperly sized, or using the wrong media for the application. This puts strains on compressors, increases energy consumption, and can reduce downstream equipment efficiency. To manage pressure drop effectively, operators often monitor it continuously via inline sensors. This allows them to detect rising resistance early and schedule for maintenance or filter replacement before it impacts production. By paying attention to baseline pressure drop values when the filter is new, teams can set clear and operational thresholds that maintain both purity and efficiency. Flow rate, which is the volume of hydrogen moving through a purification system over time, directly influences how effectively contaminants are removed. In most hydrogen filtration systems, flow rate is expressed in standard liters per minute or standard cubic feet per minute, normalized for temperature and pressure. The correct flow rate ensures that hydrogen spends enough time in contact with the filter media for proper particle capture while maintaining the throughput needed for production demands. If the flow rate is too high, the gas may pass through the filter too quickly, reducing the chances of capturing fine particulates or aerosols. This is often called media bypass, where contaminants physically slip past the wire mesh. A flow rate that is too high can cause operational inefficiencies, such as underutilizing equipment capacity or increasing system residence time beyond optimal process parameters. Balancing flow rate also prevents damage to the filter itself. Excessive velocity can stress the filter media, leading to deformation, rupture, or early clogging. Conversely, inefficient flow may promote uneven loading, where contaminants concentrate in certain areas of the filter rather than distributing evenly. Both scenarios can shorten filter life and increase maintenance costs. For hydrogen purification systems, the ideal flow rate is determined during the design phase, based on system capacity, filter specifications, and purity requirements. Operators often rely on flow meters and automated controls to keep within target ranges. This ensures not only consistent hydrogen purity, but also optimal energy usage and filter performance. Maximizing the efficiency of hydrogen filtration systems requires more than just selecting the right filter type. It also depends on how that filter is operated and maintained. Proper optimization balances filtration performance, flow consistency, and service life, helping operators achieve target purity levels without excessive energy use or premature replacement. One key strategy is selecting filter media designed for specific contaminants present in the hydrogen stream. For example, woven wire mesh offers durability under high pressure conditions, while depth media can capture finer particles at the cost of slightly higher pressure drop. Matching the filter material to the operating environment reduces stress on the system and prolongs filter life. Regular monitoring of both pressure drop and flow rate is equally important. A gradual increase in pressure drop often signals that the filter is loading with contaminants and approaching its capacity. Replacing or cleaning the filter before it becomes overly clogged prevents flow restriction, reduces strain on pumps and compressors, and avoids sudden system downtime. Flow conditioning, such as using pre-filters to capture larger particles, can also extend the lifespan of primarily purification filters. This stage filtration approach minimizes fouling and ensures more consistent performance throughout each service cycle. Ultimately, the most effective hydrogen purification systems treat filter optimization as a proactive process, using performance data and maintenance schedules to maintain efficiency, reducing operating costs, and extending equipment longevity. Thanks so much for watching. watching. If you have any questions, click our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things WS Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.